I hope in the last lecture we discussed uh, root finding methods, which are one is bisection, other one is regular function, right? So if you observe those two methods, there is one thing common. That is, every time we are finding an interval a comma b, which contains the root, and every time you need to make sure what is the interval. Like in the first step, you may have a naught comma b naught. This is the interval, and in the second step, you may get a1 comma b1, and this a1 or b1 may be equal to one of the a naughts or a naught or b naught. Okay, so like that, every time you need to carry the interval. So you need to find the interval first, then you are finding the next approximation. That is how the bisection method or regular function method is carrying out, right? Now there is a question, like without carrying this interval, can we approximate the root of the function? So that is a question here. Like given a function f of x and an equation. Now the question is to find or approximate root of this function. All right. So now you should not find the interval every time like the last time, right? So first you can do one thing. First of all, you can locate where the root is approximately. Maybe if it is a root, like maybe by finding interval only, you can see where is the root, right? For example, if I have x square minus 3 equal to 0, all right, you know the root is root 3, but let's say I want to find it out. So what shall we do? So you may substitute f of 2, that gives you 1, which is positive, and whereas if we substitute f of 1, which gives you minus 2, is negative. All right, so we are very sure that between 1 comma 2 we get a root from this interval. That is, if we assume this is f of x, so there exists some xi such that this f of xi equal to 0. Okay, initially you can take interval 1 comma 2 or a comma b. All right. So once if you pick up the interval, now you do one thing. You randomly pick up any point from this interval. Now using that point, we need to get a sequence, that is x1, x2, and so on xn, so that converges to the root side. So now can we have that kind of method now? All right. Now how to convert a problem here, a root finding problem, to a problem which simply involves in the iteration, not on the interval. Okay. So here the idea is, given a function, let's say if I give you f of x equal to, I hope in the earlier class we have solved it, x into e power x minus 1. All right, and I asked you to find the root of this equation. So now how did we do it here? Like directly we found the interval first, and later we applied either bisection or regular function. Using that we found it, right? So now what I'll do is, instead of finding that way, so it is same as finding a point. Okay, so at which this is equal to 0, right? So this is equal to 0. So this implies, means x into e power x, we wanted this to be equal to 1. So now you can do one thing. You can take a line y equal to 1, and then you can take the plot of x into e power x. Okay. So now you can actually see where they intersect. So that intersection point is nothing but the root of this line. Okay. So now similar to it, we are going to convert the problem. So now instead of writing x into e power x minus 1 equal to 1, now I would like to write x. I'd like to write it this way: x equal to e power minus x. Okay. So now what happened? It is enough to find a point xi at which xi equal to e power minus z. So if they are equal, then what happens? This one actually uh, expressed this way, right? Xi into e power xi will be equal to 1. This implies xi into e power xi minus 1 equal to 0. All right. So now, given a function f of x equal to 0, and you try to convert into this form, x is equal to phi of x. Yeah, what is it exactly we are doing here? So let me explain. So you have some function f of x equal to 0, and okay, and I'm converting this function in this form, that is x is equal to phi of x. Okay, now I hope you can draw the graph of x. So this is the graph of y equal to x. And similarly, you may have the function phi of x. Maybe let me take it like this. Now, okay, to see it clearly, let me use different colors. So you have seen the graph of phi of x in green color and x in red color. All right. So try to understand one thing. F of x only we converted this way. Okay. For example, if you have some function like x square minus 2x plus 1 equal to 0, and you have a freedom to write this way also, right? It can be expressed as x equal to x square plus 1 by 2, and not only this way, you can actually write x equal to square root of 2x plus 1. If you know x is taking only positive values. Alright. I mean, I kept x square this side and everything other side, then after it I we squared. Okay, so we can express the given function either in this form. It is also looking like phi of x is equal to x, and this one also is looking like x equal to phi of x. Alright. So given a function, you try to convert into this form. Now, the root of this equation is same as finding a point x0 which satisfies this equation. Now, finding this kind of point we call it is a fixed point problem. Okay, so we are finding a fixed point. It means we are finding an x where phi of x is equal to x. It means for phi, for this function, y equal to phi of x, that is y equal to phi of x, this guy is a fixed point. Okay, now let us see how to approximate that point. Now initially you start with an approximation x naught. Okay, now where is x? What is phi of x naught? Let me see. What is phi of x naught? Now to see phi of x naught, what can you do? You can actually go to this location because, sorry, let me change the graph a little bit so that it is comfortable. Let me have this. Alright. So now I can simply do one thing. You pick up an initial approximation. Let me assume that is x naught. Okay. And I would like to see what is phi of x naught. So to see phi of x naught, first you go to this location. Uh, the problem is, yeah, it's not converging. All right. Yeah. Okay. First, let me start with this example. So So if I pick up x naught here, all right. So this is what phi of x naught. Here. So this is what exactly phi of x naught. All right. Now I want to take this phi of x naught as my initial approximation x1. Okay. Now how to locate this x1 on the x-axis? So where is it x1? So now to see that x1, what do? You come here because this is the point where if y is phi of x naught, then definitely x is also phi of x naught, because this is the line y equal to x. Both x and y coordinates will be equal. All right. Now I want to see x1, that is nothing but phi of x naught. So you do one thing, you just come down like this, because this is where this is the point phi of x naught comma phi of x naught. This will be equal to x1. Okay. So next, again, you do the same thing. You take x2, that is phi of x1. Okay. So phi of x1 is here. This is phi of x1. Now to find it, where is x2? You just come here and come down. So this is what x2. So similarly, if you proceed that way, what happens? Slowly x3. So you started here and you are moving towards this fixed point. We are moving towards the root of the function. Okay. So here we got a sequence that is xn plus 1 equal to phi of xn that converges to the root of the function f of x, or that converges to fixed point of this function phi of x. Yeah. Now the question is it always true for all choices of phi, or is there any restriction? Okay. So definitely there is a restriction. Okay. To understand that, let me explain with one more graph. You take this and that's here, right? And then look at the function. Okay, now this is the fixed point. All right. Now let me do one thing. Let me start. So our aim is to find this xi, to approximate this xi. Okay. So if I use this sequence, that is xn plus 1 equal to phi of xn, let me see what happens. Where this is what phi of xn, and this is what the line y equal to x. I hope you can see that. Now you start with an initial point. The initial point here is x naught. All right. You see, where is phi of x naught? Where is phi of x naught? Here. All right. So this is what phi of x naught. Now I want to take x1 as phi of x naught. So you come here to this line, and this is the point, and this is the point. I can say x1 comma x1, where x1 is nothing but phi of x naught only. All right. Now to locate it on the x-axis, you do one thing. You just come down. All right. So now this is what x1. Okay. Now if I go for one more step, what happens? And this goes up. That means just other color. So somewhere here you will be, and the graph actually extends. Assume the graph is like this. Now the next approximation is here. So what happens to the next point now? So you'll go here and you'll come down. And this is x2. So in this process, what is happening? The root is here. Instead of moving towards the root, you're actually moving backwards. It means whatever sequence we are getting here, that is x1, x2, x3 and all, this is not moving towards the root. It is not converges to z. Okay. So now if you see for the condition at which this converges to z, the condition is nothing but the slope of this function phi has to be less than 1. Absolute value of the slope, that has to be less than 1. In that case only, this sequence converges to uh, the root. So this is the condition we need to have. That is phi dash of x has to be, its absolute value has to be less than 1. Yeah, you may ask where it has to be less than 1. Why? Because there may be some places it is less than 1 and there may be some places where it is greater than 1. Okay. So now where we need here is, like, you know the interval of root, right, where it lies. Initially you can find it using intermediate value theorem. So first you find out the interval where the root lies. Okay. Maybe I found out this is what the interval where the root lies. Okay. So from this interval only we are going to pick up the initial approximation. Okay. So you make sure that at least in this interval, which where you are picking the initial approximation, there the slope of this phi dash of x is, sorry, the slope of phi of x is less than. Okay. It means, for example, if you found out the root is in between 0 and 1. Okay. So while writing x equal to phi of x, you make sure that the derivative of phi of x is less than 1 in that interval 0, 1. Suppose if you find that at some portion it is, let's say, from 0 to 0.3, it is more than 1, but 0.3 to 0.1, it is less than 1. Okay, so in that case, if you believe that the root is here using intermediate value theorem in this interval, now you okay, this interval is enough, and you pick up your initial approximation from this interval only. Don't pick up from the other place where the derivative is not less than 1. Okay, so if you observe this method only involves picking up an initial term. Once if you pick up an initial term and writing the function in this form, then it is very easy. Just keep on substituting the things only. Okay, so now let us see a theorem where it says that when the sequence obtained in iteration method converges to the root. Okay, so I hope you can see it. So it is saying that when the derivative of phi dash of x, the derivative of phi of x is less than 1, absolute value, then only the sequence converges to the root. So, okay, where they have written 2, right? Let me write what is 2. So that is nothing but xn plus 1 equal to phi of x. Okay, so let's see how to estimate the error also here. So to estimate an error, we will take the approximate exact root and an approximated root, and we see the difference between them, isn't it? So now at exact root, we know that xi will be equal to phi of xi, no? So that we have written here, and you know what is the formula for xn? Xn will be equal to phi of xn minus 1. Okay. So using Lagrange's mean value theorem and inequality, so this k is nothing but some phi dash of c. That's what a k here. I hope you know the Lagrange's intermediate value theorem, that is f of b minus f of a divided by b minus a. Yeah? And you know this is equal to f dash of x. Alright. Now here what we are doing is we are f dash of c where c is in between a comma b. That is what Lagrange's mean value theorem. Okay. So we wish this slope to be less than 1. It means this is what we are expecting. Actually, you can take this b minus a to the other side, so you can write this. All right. So using Lagrange's mean value theorem, you can write this inequality. So after some simplifications, okay, after some simplification, you can see what is the accuracy in the process. Here, we don't know what is the exact root. Okay, so if you don't know the exact root, then what, instead of finding the exact error, we look for the accuracy, how accurate our iteration process is. So now in bisection method, you actually have an interval. So you're simply seeing the length of the interval and you're seeing that accuracy. But here, to see that, what we will do is we will assume that xn is the exact root and xn plus 1 is an approximated root, and xn minus 1 is an approximated root, and we see the difference between them because we don't know what is exact root here. No. So whatever last step we obtain, that is what we will take it as a root. Okay, we will take this as xi and this is the approximation, and we see the difference. So if you see this difference from the above calculation, you can actually write it this way: 1 minus k by k into phi dash of epsilon, where epsilon is nothing but the error that we need, or the accuracy that we need. If you want an epsilon accuracy, it means the distance between the exact root and approximated root, we wanted this to be less than epsilon. So from the above guy, we can actually write, if you want the accuracy to be epsilon, you can actually do the iterations until you get the difference between xi and xi plus 1 is less than this quantity. Now what is k here? The k is nothing but phi dash of x. It's not only phi dash of x, you'll actually pick up minimum of it. Okay, so let's do one thing. Let's go with the problem. Okay, here let me write what is k, because I think here it is not written right. K will give you, so you need to see the minimum of phi dash of x over the interval. So that is what k here. Okay. Now let's walk with the problem. So find root of an equation using iteration method. Here it is not mentioned. So using iteration method, we are finding the root. Where iteration method is nothing but given a function f of x, and you express this function as x equal to phi of x in such a way that the derivative of phi dash of x is less than 1, at least in the neighborhood of the root. Okay. Anyway, here they gave the interval 0, 1, so we can write for phi of x so that its derivative is less than 1. All right. Now let us see how to do it. So given this guy, you can actually have two choices. I mean, x square plus x cube plus this minus 1 equal to 0. We can write it like x cube equal to 1 minus x square. Now this implies x equal to 1 minus x square whole to the power of 1 by 3. Okay. So now for this choice of phi of x, what is phi of x here? Phi of x is nothing but 1 minus x square whole power 1 by 3. Now the question is, what can you say about its derivative? Let's see, phi dash of x. So you know that is 1 by 3, 1 minus x square whole to the power of 1 by 3 minus 1 into minus 2x. Okay. Now this one is actually minus 2x by 3 into 1 minus x square whole power 2 by 3. Okay, this is what phi dash of x. Now the question is, if this value, like I mean phi dash of x value in this interval 0 comma 1, if it is less than 1, you can go with it. You can go with this function. Otherwise, we don't go. We need to find phi of x in a different way. So let me check. Let me check. 1 I cannot substitute because I'm getting 0 in the denominator. Okay, so let me do one thing. Let me substitute x equal to 0. So that is phi dash of 0. Let me see. So that is nothing but we are seeing anyway absolute value. It becomes 0 because 0 is here. No? It's nonsense. Alright, so no issue. We are getting 0 here. No problem with it. Now let me see at some other random point, that is x equal to 0.7. So if I take x equal to 0.7, what is phi dash of 0.7? Can someone calculate and tell me? So I'm seeing its absolute value. This is what you need to calculate. 2 into 0.7 by 3 into